Okay, so if you missed class today, this is a brief overview of what we talked about. The big idea here is that what we found in lab was that it didn't really matter whether you have a soccer ball or a golf ball or a tennis ball. When they fell, the mathematical models were all the same. Another way to think about that is like this. If you had a small rock and a really big rock, and you dropped them at the same time, they would both hit the ground at the same time. So they would both fall exactly the same rate. And so we call this the acceleration due to gravity. Gravity causes the rocks to fall down, to accelerate downwards, and they go faster and faster and faster. And it's the same whether you're a small penny or a big rock. So what that means is that we can find the acceleration due to gravity. And so in lab, we got some mathematical models that look like this. The distance the golf ball or the tennis ball or the soccer ball fell was equal to somewhere in the neighborhood of 5. It was -5 times t squared. That was the mathematical models we got. Now, we're going to compare that to the equation that says the distance an object will fall, delta y, is equal to v naught times t plus 1/2 a t squared. And if the initial velocity is 0, we can get rid of that term, then this really just becomes the distance an object falls, delta y, equals 1/2 the acceleration times the time squared. And so by comparing our two equations, the mathematical model from our lab with our equation from our theory, these are both distances, the distance it falls, there's time squared. That means that the -5 must be 1/2 the acceleration. And so if the -5 is 1/2 the acceleration, then of course the acceleration itself must be around -10. The units are going to be meters per second per second. And we're going to call this the acceleration due to gravity. So this is the acceleration due to gravity. And that's a rather important number. Now, when we do calculations, we're actually going to use this. The acceleration due to gravity, if we are very precise, we can actually measure it to be -9.81 meters per second squared. And when we do calculations, we're going to use this value. But right now, let's just think about this -10 for a minute and what it means. So when gravity is acting on an object, it's going to decrease the velocity of the object 10 meters per second every second that goes by. So imagine we take, here's the ground, we take a soccer ball and we kick it upwards really hard so that the initial velocity is plus 30 meters per second. It's going upwards at 30 meters per second. As soon as it leaves your foot, gravity is the only force acting on it. So what will happen? Well, it will go up, but it'll slow down and eventually stop, and then it'll come back down. And so if we make a little table of the time and the velocity, at the beginning of our problem, t equals 0, our velocity was 30 meters per second. But after 1 second has passed, gravity will decrease our velocity by 10 meters per second every second. So after 1 second, now we're only going 20 meters per second upwards. The ball was going up fast, now it's slowing down. After 2 seconds, gravity will decrease this again, 10 meters per second. So now we'll be going, instead of 30 and then 20, we'll be going 10. And after 3 seconds, the velocity will be 0. Now remember, this is the velocity. It's at the tippy top right here. It's not moving. It's not on the ground, but it's stopped moving upwards. If we wait another second, the velocity will be -10 meters per second. And after 5 seconds, it will be -20 meters per second. And after 6 seconds, it will be -30 meters per second. So what gravity is doing is it's decreasing the velocity by 10 meters per second every second. It doesn't necessarily mean it goes direct down right away. You might throw something up, but gravity will slow it down until it stops it, and then it'll go down. If I were to drop a ball from really, really high and it were to fall for 7 seconds, it would be going negative 70 meters per second because the velocity decreases 10 meters per second every second. Okay, so that's the big idea of what we talked about today. It doesn't matter whether you've got a penny, whether you've got a rock or a truck. Anything that is falling, as long as we can ignore air resistance, anything that is falling will accelerate downwards at negative 10 meters per second squared. Okay? Now, when we solve problems, we're actually going to use this negative 9.8. And it actually is so important in physics, it gets its own letter. So 9.81 meters per second squared gets called g. And then we can actually say that the acceleration due to gravity is just negative g. So you will see in calculations, we're going to use negative 9.81. It's not quite 10, but it's close. When we sort of are thinking conceptually, we're going to use 10, negative 10. And when we're solving problems, we use negative 9.81. So if you look online, there is also a video link below the link to this file, or over on the right where it says resources. There's a link that says a video example problems. So we solved 3 example problems in class where we used this idea of an acceleration and solved problems of objects in free fall. So an object is in free fall if gravity is the only force acting on it, and if we have gravity is the only force acting on it, we have a freebie. We will always know the acceleration is going to be negative 9.8. You want to calculate it, you want to figure it out. If gravity is the force that's causing the velocity to change, the acceleration will always be negative 9.81 meters per second squared. So watch the video on the example problems. That was the second part of the lecture that you missed, and that will help you see how to solve the example problems.